Hello and welcome. I'm Dr. SeyedMostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome everyone. Let's dive into this fascinating realm of computer architecture and parallelism strategies. We're talking about deep learning for intrusion detection and the underlying hardware, including pipelines, math coprocessors, VLIW, multi-core, and hyperthreading.
Absolutely. It's really an intriguing mix of software and hardware interplay. So, where do we start?
Let's begin with the big picture, parallelism. We see strategies like MIMD, which is multiple instruction, multiple data. Essentially, it's about, running many things at the same time, like in a pipeline.
Right. And if we think about pipelining, it's like a production line for instructions, where each stage, such as fetching, decoding, and executing, passes information along to the next stage.
Exactly. It's like you have this continuous flow where the output of one task is the input of the next, sort of how assembly lines work in factories.
And isn't it fascinating that in a CPU, this pipelining enables instructions to overlap? Basically a form of parallelism at the instruction level.
For sure. This idea of instruction-level parallelism is what you see in single-core superscalar processors. They can reorder instructions, split them into micro-instructions, and do aggressive branch prediction. It's like having multiple mini-processes happening in tandem.
That's a neat way to put it. So, by fostering this parallelism, processor speeds have increased so much over the years, right?
Yes, basically. And moving on, we have the math coprocessor, a special chip that used to handle more complicated mathematical operations.
Yeah.
Remember those pre-Pentium days? When the ALU was mostly good with whole numbers, a math coprocessor stepped in for those complex tasks.
Right. And today, we see a similar role emerging with GPUs acting as SMT, or single instruction, multiple data, math coprocessors. They especially shine in tasks like graphics rendering and, of course, deep learning computations.
Absolutely. It's like imagine thousands of tiny workers calculating in parallel, which is why GPUs can handle massive amounts of numerical data so efficiently.
Yep. Speaking of GPUs, the content even mentions some video examples explaining how graphics cards operate. Those demos really bring the idea of GPU versus CPU into perspective, wouldn't you say?
Definitely. The visual demos and Mythbuster-style experiments make it crystal clear. While the CPU might be like a focused expert, the GPU is more like a huge crowd of eager preschoolers all jumping in to perform basic arithmetic tasks at scale.
That analogy really paints the picture. Now, shifting gears a bit, let's talk about VLIW, or Very Long Instruction Word. This concept takes advantage of a huge amount of instruction-level parallelism, right?
Yes, indeed. VLIW architectures, which emerged in the early 1980s, package multiple operations into a single very long instruction. It's like bundling several tasks together for simultaneous execution.
And because these processors have multiple functional units sharing a register file, the compiler does the heavy lifting, checking for data dependencies before scheduling the parallel dispatch.
Exactly. It's interesting because, on one hand, this reduces hardware complexity, so you save power. But on the other hand, It means you have to rely on very complex compilers to get everything scheduled just right.
I get that. But don't you think that relying so heavily on compilers sometimes creates a bottleneck? I mean, the complexity can be a real challenge.
That's a fair point. The compilers need to be extremely sophisticated, which can be a drawback. Plus, you get increased code size as a trade-off, which puts more pressure on memory bandwidth.
And speaking of memory, the multiprocessor systems discussed here, with multiple sockets, even tie into this conversation. There are boards with 2 processors and dozens of DIMM sockets, each playing a role to boost performance.
Yep, and that's where infrastructure design becomes so interesting. Having multiple cores and multiple processors means you can process even more instructions simultaneously. Some boards even have PCIe NVMe drive bays, which is insane when, handling data for deep learning intrusion detection tasks.
Absolutely. It highlights how every layer, from the top-level architecture down to individual instruction scheduling, plays a critical role.
And another key concept we need to touch on is hyperthreading, or Simultaneous Multithreading, SMT. With SMT, each physical core can handle multiple threads, making the OS think you've got more virtual processors than you physically do.
Right. Although one must note, it's not really true parallelism because the resources are still shared, unlike in multiple cores where each has its own copy of the resources.
Exactly. It's a clever technique to maximize utilization by allowing another thread to use idle resources, while one thread is waiting on something like a floating point operation.
That strategy is really remarkable, yet it sometimes faces criticism because of the overhead in managing those threads effectively.
True, but overall, it's been a major boon to overall CPU performance without needing additional physical cores.
Yep. Now, what do you make of those clever analogies that compare compilers and operating systems to crews solving optimization problems? I thought that was a pretty vivid image.
Oh yeah, it's like, consider the compiler as a team of experts, meticulously planning out every move. While the OS is like a busy warehouse crew trying to get the job done, then the CPU is, the worker that actually carries out the tasks. And the GPU is like 1,000 little helpers chipping in. It really brings the whole system into focus.
That analogy really drives home how intricate and well-coordinated the process has to be. It's almost as if every component is playing a role in a grand, high-performance symphony.
Exactly. And I find it fascinating how these different strategies, pipelining, math coprocessors, VLIW, multiprocessors, hyperthreading, all converge to make modern computing so efficient.
Yes, and to think that all this functionality is what underpins everything from gaming graphics to complex deep learning models for intrusion detection. It's just mind-blowing how these innovations tie together.
I know, right? It's like every time you use a computer, whether for simple tasks or complex analyses, you're benefiting from these intricate layers of design. Even deep learning algorithms for detecting network intrusions run thanks to these powerful foundations.
Speaking of which, do you think that the approach of using deep learning for intrusion detection could be significantly boosted by leveraging these hardware strategies?
Absolutely. It's like, imagine deep learning models that continuously refine their detection abilities while running on hardware that's sliced into parallel segments. Each segment optimized for a certain type of operation. It ensures data is processed fast and threats are flagged quickly.
Right. However, one could argue that the complexity in scheduling and managing these parallel instructions might sometimes lead to inefficiencies if the software isn't designed to handle such intricacies.
That's a good critique. I mean, it's a double-edged sword. While the hardware is capable of tremendous speeds, if the software doesn't perfectly leverage these capabilities, you might not get the full benefits. It's like having a sports car, but driving it in first gear most of the time.
Yeah, Exactly. And that's why advancements in compiler design and system software are so critical. They have to evolve alongside the hardware to truly unlock those performance gains.
Totally. And this interplay is really what drives innovation in computer science. From deep learning algorithms enhancing security measures to cutting-edge parallel processing architectures, each component pushes the envelope further.
It's really an exciting time to be immersed in these technologies, especially with all the rapid advancements we're seeing across both hardware and software domains.
Absolutely. And you know, while we've talked a lot about the nuts and bolts of parallelism, it's interesting to see how these ideas ultimately impact everyday computing artifacts, from smartphones to massive servers handling deep learning for intrusion detection.
Yes, definitely. It's a reminder that every innovation on a chip has a ripple effect across all layers of technology.
Right? And well, as we wrap up this discussion, it's clear that the evolution of parallel processing, pipelining, VLIW, SMT, is fundamental to our modern computing experience. The challenges and trade-offs, like those in VLIW with compiler complexity, really highlight how intricate the balance is between performance and efficiency.
Absolutely. Agreed. And as deep learning continues to grow and tackle, say, intrusion detection, these hardware strategies will only become more relevant. It's been a pleasure diving into these details today.
Indeed it has. Kudos to the engineers and researchers who push these boundaries. Until next time, stay curious and keep exploring the marvels of computing.